In chapter number 10, we're going to deal with general circulation. So we're going to switch gears and talk about some of the larger features of atmospheric sciences. In the book, pages 265 to 291. Okay, objectives. We're going to spend a lot of time on this thing called the three-cell model. And we're going to take a look at the various components on this particular model. There'll be a lot of words, a lot of latitudes that you're going to have to get to know and memorize. Notice in these objectives, the first page and this particular page and the third page all refer to items that we're going to find on this three-cell model. So with this video, we'll be spending a lot of time talking about those various features. And then eventually we'll switch into talking about the jet stream. We'll talk about two different components, the polar jet stream and the subtropical jet stream in the upper atmosphere, and then another jet stream that's considered to be low level. And then we'll end the chapter with the talk on the currents, and we'll also talk a bit about the teleconnections like El Nino and La Nina. Okay, so to get us started, here we can see that we have a picture of a full disk view from a geostationary satellite system. This one is concentrating on Africa and Europe. So notice we have a distinct band of clouds located through here, and that line is roughly associated with the equator. So we have clouds associated in that area. And then up here in northern Africa into the Middle East, you can see there's a lack of clouds. So maybe a drier part of the world. And then up here, when we get into Europe, we have some clouds again. And then it's too far to see up on the top. But what I'm getting at is you can see that there's distinct belts of clouds, no clouds, clouds, and then most likely not much in the way of clouds right at the North Pole. So this is setting us up for the three-cell model. So in the world we do have distinct areas of deserts. We do have a distinct area that we call the tropical rainforest, and then up in northern Canada we also have the area called the tundra. So what we're referring to is the general circulation of the world. The average airflow around the globe caused by unequal heating of Earth's surface acts to balance the radiative energy budget. So what we're getting at is, remember from our earlier chapters, the equator receives on average more incoming solar radiation throughout the year than outgoing infrared radiation, so they have a surplus. And once we got north of about 38 degrees latitude, excuse me, then we switched. And then we had a deficit. So areas north of 38 degrees north and or south latitude, they had a deficit. So throughout the whole year, they would lose more energy than they would gain on incoming. So there's the imbalance in play. So what we're going to do is we're going to take a look at the single cell model first of all, and we're going to make some really big assumptions. First of all, the Earth's surface is all water, so therefore we don't have to worry about the different specific heat values between land and water. The Earth axis is not tilted, so if that was the case, everybody would get 12 hours of daylight and 12 hours of sunlight year-round. And the Earth does not rotate. Now that's the biggie. The Earth does not rotate. So if we had these assumptions in play, all that you would see we'd have one big thermal direct cell, and that would be called the Hadley cell. So this is what it will look like, the general circulation of the world under those three assumptions. So the equator would be a belt of low pressure, so air would be converging into the center of the lows. And then the air above the lows would be rising, as you see here. And then that air would take off and work its way up to the north and or south pole. In this case, I'm pointing at the south pole. And then it would descend over the polar regions. And the air would be diverging away from the high pressure center. So that's all you would have. is low pressure at the equator, high pressure at the polar regions, and this thermal circulation cell, the Hadley cell, stuck in between. So pretty simplistic. Okay, now when we talk about some of these regions on the Earth, whenever I use the word tropical, I'm referring to about the equator to about 15 degrees north and south latitude. Subtropics about 15 to 30 degrees north and or south latitude. The mid-latitudes, that's where most of the United States is located, is between 30 and 60 degrees north latitude. Subpolar regions, 60 north to 75 north, and the polar region, 75 up through 90 degrees. So just some of the terminology that we might be using in this particular chapter. Okay, the three-cell model. Here are the assumptions. We're still going to keep the Earth covered with water, so we'll have equal heating of the surface. The sun is still going to be over the equator, so the tilt in the axis is straight up and down. No tilt is what I should say. But we're going to allow the Earth to rotate. So that's the only difference between the single cell model and the three-cell model. We're going to allow the Earth to rotate. So here's what the general circulation would look like with the Earth rotating. And notice it's a lot more complicated than the single cell model. So let's take a look and start at the equator and talk about some of these words and some of the latitudes where these particular belts of pressure are located. So on the equator, note we have the L's. So the equator is a belt of low pressure systems, and we know that low pressure systems, the air is converging into the center of the low down on the surface, and then within the low pressure system we have rising air. So that combined will cause upward motion in the atmosphere, and that could cause some precipitation to develop along this particular zone and or belt. Therefore, you do have a lot of thunderstorm activity along the equator due to this belt of low pressure systems, and this is where you would find the Earth's tropical rain forest. Okay, some of the names for this region: doldrums, equatorial low region. This is probably the one I use the most, the intertropical convergence zone, ITZ for short. Okay, let's move upward. Between the equator and 30 degrees we have wind belts. In the northern hemisphere it's the northeast trade winds, southern hemisphere the southeast trade winds. Now note the curvature as we come from this area working our way towards the equator. Can you see that the curvature is to the right? In the southern hemisphere the curvature is to the left. So this shows us that the Coriolis effect is in play with these winds. Again, Coriolis, apparent deflection to the right in the northern hemisphere and to the left in the southern hemisphere. Okay, so these are the trade wind areas. Okay, moving up 30 degrees north and or 30 degrees south latitude. Now we flipped. We were low pressure at the equator. Now we have high pressure at 30 degrees north and south latitude. So this is the subtropical high region. So the makeup of the high pressure system was air diverging away from the center of the high and downward motion into the high pressure system. So high pressures are more noted for clearer skies because of divergence and sinking air from above. So guess where the major deserts of the world are located? In the subtropical high regions, right around 30 degrees north and 30 degrees south latitude. So the northern Africa fits into this zone, the Middle East fits into this zone, and in the southern hemisphere you'd have to take a look at the country of South Africa and the country of Australia. They fit in the zones of subtropical highs 30 degrees south latitude. Okay, moving on. The westerlies, that's going to fall in between 30 and 60 degrees north. So most of the United States will fit into this area. So we are in the westerly wind belt. Our prevailing wind here in Grand Forks, remember, was from the northwest. So most of the prevailing winds will have a westerly component to it because of this wind belt. And then this important feature up here at 60 degrees. So now we have another pressure belt, and it is going to be a low pressure belt at 60 degrees north and 60 degrees south. So we call this one the polar front region, the polar front low pressure belt. Now for us in the United States and in Canada, this one is what we have to monitor for our changing weather conditions, because this low pressure belt is going to shift with winter and summer, and as it works its way back and forth through our part of the country, it can give us some pretty active weather, including some of our snowstorms in the winter season. Okay, moving on, between the 60 and up to the North Pole, we have another wind belt called the polar easterlies. And then right at the North and South Pole, you can't see it here, but the North and the South Pole is a high pressure region. So diverging air and sinking air from above. So think about it. If this high region was desert, what do you think? Is this high region also going to be desert? And the answer is yes. So this is just considered a cold desert. The North Pole and the South Pole do not receive much in the way of snowfall throughout the year because they are associated with a high pressure belt. So that is the three-cell model looking at the surface features. And then off on the left-hand side, you can see how the arrow is rotating above the surface. So upward motion here due to the convergence. And then we carry it upward and it descends at 30 degrees. So this circulating cell is called the Hadley cell. Above the mid-latitudes, we have the Ferrel cell in play. So that one's kind of hovering above the United States, the Ferrel cell. And between 60 degrees and the North Pole, we have the polar cell rotating. So those are the three various cells on this three-cell model. So a lot of questions can be derived from this one particular slide, so make sure you pay a good amount of attention and know the names of some of these belts, know which latitudes are associated with low and high pressure, and then we'll add on to this here in a bit. Okay, so next on the list is talking about some of the pressure systems at these various belts. And we're going to talk about initially the synoptic systems. We're going to concentrate on the Pacific High and the Bermuda High, the Aleutian Low, and the Icelandic Low. Now the key thing here is the first pressure systems are going to be synoptic systems. The reason I'm making that statement is we also talked about a feature called a thermal low and high pressure system. So these first ones, these four, are going to be considered synoptic in nature. So a little bit of review. When we had a synoptic low pressure system or cyclone on the surface map, they were often associated with a trough on the upper level charts. So here's the trough on the upper level chart, and if you go down to the surface chart, there's your area of low pressure. High pressure on the surface, anticyclones, they were often associated with a ridge on the upper level charts. So here's your ridge working through here, and if you go down to the surface, there's your high pressure system associated with that ridge. So these are a synoptic low and a synoptic high pressure system because they have support from features in the upper atmosphere. Trough with the low, ridge with the high pressure system. So we have these features on the map, and identified those that will affect the North American continent. The Aleutian Low is located in the Gulf of Alaska in association with the Aleutian Islands off of Alaska. The Icelandic Low is typically located up here between Greenland and Iceland. The Pacific High, obviously in the Pacific Ocean, and the Bermuda High, kind of centered around the small island of Bermuda in the Atlantic Ocean. So these are, excuse me, considered the semi-permanent synoptic systems. Now we're looking at winter on this one. Note the strength of the Aleutian Low and the Icelandic Low, the Pacific High, and the Bermuda High. Also note the location of these features, because the next slide I'm going to flip and I'm going to show you summer. Are you ready? Here comes the summer slide. See what happened? Where's my Aleutian Low? Why is the Icelandic Low so much weaker in the summer season? Now it seems like the Pacific High and the Bermuda High have gained strength. So let me toggle back to winter and look at some of the isobars, some of the numbers associated with these low pressure systems and high pressure systems. And then let's go forward into summer. So you can see there's a dramatic increase in strength of the synoptic low pressure systems, but there is a gain in strength of the synoptic high pressure systems once we move into the summer season. Now, why do you think that is? Why are the lows dominant in the winter and the high pressure systems dominate in the summer? Well, it goes way back to this. The lows on the surface are associated with troughs in the upper atmosphere, and the high pressure systems on the surface are associated with the ridges. Which of the trough and or ridge was associated with cold air aloft? It's the trough. So therefore the ridge is associated with warm air aloft. Now let's go back to winter. So if we're in winter mode, do you think we have a lot more cold air in the upper atmosphere? Yes. So what features become dominant in the upper atmosphere? The troughs, since they're associated with the colder air. So they can support the synoptic low pressure systems. Now when we flip to summer, the northern hemisphere is going to warm up, not only on the surface but in the upper atmosphere as well. So since we have more warmer air aloft, then the ridges become a little more dominant during the summer season, and then they can help support the synoptic high pressure systems on the surface of the earth. Now, why do we need to know all this stuff? Well, if we take a look at forecasting and or I should say outlooks of weather patterns in a certain time of the year, we basically need to know the strength of these particular semi-permanent features and their locations, because they can help us aid in dictating what a weather outlook might be for a certain part of the country. To give you an example, this Aleutian Low, that's its typical location. If this low was located here instead of there, well, that means the circulation is going to be further south pulling in. So this could cause more precipitation along the western coast of the United States, because if that's shifted, then that high pressure system might be shifted as well. So that could open up more precipitation for areas like central and southern California during the winter season. Another one that I like to pick on is switching to summer. Unfortunately, we don't get a chance to talk much about hurricanes in this particular course, but hurricanes can start development with just waves of energy coming off of Africa moving in this direction with the trade winds, and as they come over the Atlantic Ocean and start to work from east to west, they can pick up strength interacting with the warmer waters of the Atlantic. So what the Bermuda High can do is be a steering mechanism for the movement of these hurricanes. I know a lot of you are a little young back in 2005, but that was a big hurricane season in the United States. That was the year of Katrina that hit the city of New Orleans, located right in this area. So why did that hurricane make it all the way into the Gulf of Mexico? Most likely because the Bermuda High was shifted a little bit south, and it had an extension of a ridge through here. And so the hurricanes, as they came across, they're unable to make that northeast turn. They had to keep on coming, and then they're able to make that turn once they got into the Gulf of Mexico. So 2005 was quite an active year. Now last year we had a hurricane that came very close to hitting the United States, but the Bermuda High kind of allowed it to turn, and it didn't come ashore until we got into the Carolinas. So Florida escaped a major blow, again, just due to the positioning of the Bermuda High and the strength of the ridge that was extending towards the mid-Atlantic states. So just to give you a little idea of how we can use these particular systems in determining things like, will California have a wet winter, and or will the United States have an active hurricane season? Okay, moving on, and the next on the list is talking about these thermal features. So now we got to flip gears. The next low and high pressure systems we talk about will be thermal in nature. So we're going to talk about the Siberian high, the Canadian high. Over in India, we'll take a look at their thermal lows that help promote the monsoonal seasons, and also the one that promotes our weaker monsoonal season here in the southwestern part of the United States. So on the map, let's review thermal features. A thermal low is only there because of a broad area of warm temperatures near the surface. In the upper atmosphere, you actually might have a ridge of high pressure above the thermal feature. And a thermal high is just there because of a broad area of colder air near the surface. In the upper atmosphere, and actually might have a trough in that vicinity. So the upper air features are just the opposite of what we had with the synoptic features. So now I'm going to concentrate on the Canadian high, which is a thermal high, the Siberian high for the winter season, and then in the summer season we'll flip to the thermal low over the southwestern part of the United States and the thermal low over here in Eurasia. So let me back up to winter. The Canadian high becomes dominant during the winter because it's a broad area of cold air. So the North American continent cools down during the winter season. The Canadian high is able to build usually initially up here in northern, over the ice pack in extreme northern Canada, and then it can shift and work its way down to the south with the aid of the jet stream winds. So this is the reason why good old North Dakota and Minnesota, we have a lot more colder days in the winter, because these Canadian highs like to invade our area quite often. Now over in the Eurasia, the Siberian high, the thermal high, note the arrows are all pointing offshore, and hence this is the dry season for the monsoon in Indonesia over through Pakistan and India. Now switching gears to summer, the continents will warm up, the thermal high pressure systems kind of disappear, and now they're replaced by thermal low pressure systems. And remember, the circulation around these is counterclockwise. So now we can start pulling moisture in from the Gulf of Mexico, and now we have onshore flow through this part of the world to give them their wet monsoonal season. So the Bermuda high rotating this way in combination with the thermal low rotating this way, that can bring up moisture from the Gulf of Mexico up into the northern plains. So we have a better chance of getting more significant precipitation during our warm season due to these two systems working together to pump the moisture up towards us. Now the Pacific high, again going back to the synoptic high, that shifted north during the summer. Note the arrows. So now that cuts off the precipitation for this part of the world. So people that live in areas like Seattle, they can get a little bit of a drier season when they get into July and August. And obviously a lot of California is completely cut off from precipitation during the summer season. Okay, so the Canadian high, here it is. This is the polar front, typically up at around 60 degrees north latitude, but in the winter it does shift south. So the cold air is on this side and the warmer air is on this side of this subpolar low or the polar front. So just to tie it in, on this map, this is, as I'm taping this, it looks like we're going to, unfortunately, here in Grand Forks, get into one more snow event in the first part of April. This is valid for 7 p.m. on Friday, and they have a mixed area of precipitation for the Grand Forks area. In fact, as I'm doing this particular video on Wednesday, April 1st, they just put Grand Forks into a winter storm watch. So those that are in the southern states, I guess you're kind of glad you're not up here in Grand Forks during this another winter storm possibility. But what I want to get to, on the surface map, we have high pressure, low pressure, low pressure. So what's what? Well, this one up here, this high pressure system, is going to be thermal. So that's a broad area of cold air near the surface. This high pressure is going to be synoptic. So that's going to have upper air support with the ridge. This low pressure system, that one's going to be synoptic, as well as the one up here, synoptic. It's too early for the thermal low to establish itself in the southwestern part of the country. Now, how do I know this? Well, let's go to the 500 millibar map and note where that surface high pressure system is located. Underneath a trough in the upper atmosphere. That's the makeup of a thermal high pressure system. How did you know this one was synoptic? On the surface. What's above it? A ridge. So that's why that's a synoptic high. This low, synoptic, because it's associated with this broad trough. This low is associated with this trough, and this low is associated with this trough. So all of the lows on the surface are synoptic. This high was thermal. This high was synoptic. Just to point out what's going to be like, and this map is valid for Friday at 7 p.m. here in local time in Grand Forks. So it's we're going to get a little bit on the cold side too. Once that snowstorm moves off, it's going to feel like winter around here for a few more days. Okay, so again, just to tie up this part of the chapter, the equator was a low pressure belt. So we had convergence and rising air, the ITCZ zone, intertropical low region, and this is associated with the tropical rainforest in Africa. 30 degrees, we had high pressure, downward motion, and diverging air. So there are the major deserts in the world. 60, subpolar low region. So now we do have a chance for precipitation events through here. Obviously not as numerous as the equator. And then right at the North Pole was high pressure, downward motion, and so the North Pole and the South Pole are actually considered cold desert regions. Okay, so that wraps up the first video. On video number 2, we'll switch gears and we'll spend some time talking about the various jet streams in the atmosphere.